Physical Science 20 Waves. Welcome to the lesson that will help you complete the assignment W4 for reflected and refracted waves. We're going to start by labeling this diagram. Normal is the line drawn at a right angle to the surface. The angle of incidence is the angle between the normal and the incident ray. And the angle of reflection is the angle between the normal and the reflected ray. This is all something that we had done in the mirrors unit. The two laws of reflection. The angle of incidence equals the angle of reflection. If we increase the angle of incidence, it will also increase the angle of reflection. It's just like in pool. If I decrease the angle of incidence, I have a smaller angle of reflection. And just like what you may have done in pool, if you shoot the ball directly towards the bumper, it comes directly back at you because the angle of incidence equals 0, so therefore the angle of reflection equals 0, and the ball travels along the normal towards and away from the surface. The second rule is that the normal, the incident ray, and the reflected ray are coplanar, meaning they all exist within the same plane. Refraction is the changing of a wave's direction when it passes into a new medium. Looking at the graphic for water traveling from deep water to shallow water, what happens to the frequency? Well, let's put some stuff in our water, and that's going to maybe help us understand what's going on. Out in the ocean, I've got a piece of driftwood, and let's say that driftwood gets hit by a wave 4 times every second. That means that 4 waves per second will be transitioning from deep water to the shallow water, which means that this buoy out in the water is getting hit by a wave 4 times every second, which means that the shore gets hit by a wave 4 times every second. The frequency remains the same. And that makes complete sense, because if I was an ant sitting on the driftwood, and let's say I got hit by a wave 150 times in 1 hour, my cousin over here on the shore would have been hit by 150 waves in the same hour, because that's the number of waves that had traveled through that medium in that time period. If I look at the wavelength, I can see that the waves have gotten shorter by looking at the graphic. So wavelength has decreased. If the frequency does not change, but wavelength has decreased, and since v equals wavelength multiplied by frequency, that means the speed must also decrease. When the slinky was pulled out to increase the tension and pulses were sent down at the same rate, what happened to frequency? Well, let's say Fresh sends down 5 waves in a second. Well, that means that green is going to receive 5 waves in a second. Let's say Physics Rocks sends down 5 waves in a second. Well, the student on this end will receive 5 waves per second. So regardless of the tension, the frequency will not change. So what happened to the wavelength? Well, the wavelength got longer. So the wavelength increased. And what happens to the speed when we pulled the slinky out to increase tension? The speed also increased. Since the speed of a wave equals frequency multiplied by wavelength, if the frequency remains the same, but the wavelength increases, the product of those two numbers will increase as well, so therefore speed must increase. Since frequency does not change when waves pass into a new medium, the following formula can be derived. The speed of the wave in the first medium is equal to the wavelength multiplied by its frequency, and the speed of the wave in the second wavelength is equal to its wavelength multiplied by its frequency. Since frequency does not change, I'm going to rearrange each of these formulas to solve for frequency. So in both cases, in both formulas, I'm going to divide by wavelength. When I divide by wavelength, the wavelengths are factored out on the right-hand side, leaving frequency to itself. So frequency is equal to velocity divided by wavelength. And since frequency in the first medium also equals frequency in the second medium, we can conclude that velocity in the first medium divided by wavelength in the first medium will equal the velocity in the second medium divided by wavelength in the second medium. Our first example is a water wave passing into shallow water. So I made a note that we are going from deep to shallow on my page. If its new velocity is 4.2 meters per second, its new velocity, it has gone into the shallow, so the velocity in shallow water will be 4.2 meters per second. So I'm going to put that in my variable list. Instead of writing V1 or V2, I used a subscript S. So velocity in shallow water equals 4.2 meters per second. And if it had been traveling with the speed of 5.4, so that's how fast it was traveling in the past. And in the past, it was in deep water. So I'm going to make the velocity in deep water 5.4 meters per second. So V subscript D equals 5.4 meters per second. And it says when it was traveling 5.4 meters per second, it had a wavelength of 3.1 meters. So that will be the wavelength while in deep water. So wavelength deep equals 3.1 meters. And it says what is the new wavelength? The new wavelength will be in shallow water. So I'm looking for the wavelength in shallow water. So lambda s equals question mark. Since we're going from one medium to another, we're going to be using the new formula that we learned today. Vs over wavelength s equals Vd over wavelength d. I'm looking for wavelength in the shallow. Wavelength in the shallow has two problems. Problem one, it's not by itself. Problem two, it's in the denominator. So the first thing I want to do is get it out of the denominator. I could do that by multiplying both sides by lambda s, or else, since I have two fractions, I can take the reciprocal of both sides. And that's what I'm going to do in this example. Now that I've taken the reciprocal of both sides, lambda s is in the numerator. I need to get velocity shallow away from lambda s, so I'm going to multiply both sides by Vs. When I do that, the Vs's on the left-hand side will factor out, and now I have lambda s by itself. So now I'll rewrite my formula. Wavelength in shallow equals wavelength in deep multiplied by velocity in shallow divided by the velocity in the deep water. Now I can substitute my numbers in for my variable list. 3.1 multiplied by 4.2 divided by 5.4 gives me 2.41. I'm multiplying and dividing. All my numbers have two significant figures, so my answer will only have two significant figures. And the last thing I need to do is determine my unit. Meters per second to meters per second will factor out. And that leaves me with meters. True story, Porter is on a baby swing. This was when he was a baby. The horizontal distance between the endpoints is 2.3 meters. It takes him 0.47 seconds to return to the lowest point on his path. First thing we're asked to find is the amplitude of the swing. Well, if we think of a swing as being a wave function, when the swing is at the bottom, that would be our rest position. When we swing all the way to the back, that would be our trough. And when we swing all the way forward, that would be our crest. So if we consider the person in the swing to be a pendulum, and they're going all the way from the back to the front. That is like going from the trough all the way to the crest. And that is half a wavelength. And half a wavelength, going from trough to crest or crest to trough, contains two amplitudes. Since 2.3 meters contains two amplitudes, I will take that number and divide it by 2 to find the value of a single amplitude. And that gives me an amplitude of 1.15 meters for this swing. We are also asked to find the period of the swing. We are told it takes him 0.47 seconds to return to the lowest position on his path. That would be half of a complete cycle. So if it takes 0.47 seconds to do half of a cycle, I will have to multiply that number by 2 to find out how long it takes to do a complete cycle. So a complete cycle then takes 0.94 seconds. Now for part B. 127 seconds pass before Porter suffers from motion sickness. How far has he traveled before he pukes? Going all the way from the back to the front is 2.3 meters, but that's only half of a complete cycle. So in one complete cycle, he travels 4.6 meters. We're told 127 seconds pass before he suffers from motion sickness, so that is our time, 127 seconds. And the period is how long it takes to do a complete cycle. And in part A, we determined that the period is 0.94 seconds. If I have period, time, and cycles, I will want to use the formula period equals time divided by cycles. I'm looking for cycles, and it has two problems right now. It is not by itself, and it is located in the denominator. So the first thing I want to do is get it out of the denominator by multiplying both sides by cycles. So cycles and cycles on the right will factor out, and I will rewrite that formula. Cycles multiplied by period equals time. Now I have cycles in the numerator. To get it by itself, I will divide both sides by period. Big T and big T on the left-hand side will factor out. I have now isolated cycles. Cycles is equal to time divided by period. Now I can substitute my numbers in. 127 seconds divided by 0.94 seconds tells me that he had completed 135.106 cycles before he puked. To determine the total distance he covered, I'm going to multiply the number of cycles by the distance traveled in a single cycle. We determined in a single cycle he travels 4.6 meters. So in two cycles he traveled 9.2 meters. In 135.106 cycles, he will have traveled 621 meters. I will correct for significant figures. Both numbers being multiplied only have two significant figures, so 621 meters becomes 620 meters. You're good to move on to the W4 assignment. To fin.